into spherical. So the integrand may be pretty straightforward. E to the rho times rho squared sine phi. Okay? So given that, when you convert that to spherical, think about what the rho expression is. It's rho squared e to the rho, like x squared e to the x. When you integrated x squared e to the x, what do you have to do? Integration by parts. But you can use that tabular method with x squared e to the x. So you do have to do by parts on this one when you integrate rho squared e to the rho. And don't cram this with by parts. It's out there. It works. What about these limits? Can you envision what that shape looks like? Z goes from 0 to this funky root equation, and it's probably too small for you to see.
The top half.
Oh, there you go. So Z goes from 0 to the top half of a sphere of radius 1. Okay, so just the Z limits gives me from the xy plane all the way up to the sphere of radius 1. So maybe it's just that top hemisphere, okay? And every point inside it. Then X goes from here to here.
Is that half a sphere this way?
Well, keep in mind, this is the two-dimensional equation. Remember the fourth that I showed you over here the other day? If you solve for y equals root 1 minus x squared, that's the top half of a circle of radius 1. So x goes from the left half semicircle to the right half semicircle, and this is a circle of radius 1. So is there anything funky about this and that? No, everything's flush so far. Everything fits just perfectly. If a sphere of radius 1 comes down to the xy plane, it'll make a circular intersection of radius 1. So far these equations gel with that one. And just those two still suggest from the xy plane to the sphere and all these points in the middle. Until you look at the y limits. Y only goes from 0 to 1. So if you had the whole thing, y would be going from -1 to 1.
So that'd be a theta.
That only affects theta, yes. Okay, so since I have the top half of a semisphere of radius 1, that guarantees rho going from
0
rho, not phi. Rho, your radius. Okay, yeah. So 0 to 1 for rho. Okay, the top half of the semisphere, just that much, guarantees what for phi? 0 to pi over 2. In all directions, you're going to have 0 to pi over 2. But then, because you only want the positive y-axis half, I think you said it. For theta, that's going to be 0 to pi. Just think about the unit circle. If I want the positive y-axis half of the unit circle, I go from theta equals 0 to theta equals pi. And that would correspond to my theta limits for this spherical. Okay. So sometimes you may not need a picture, but you can kind of reason it out. If you remember some of these equations, I've tried to make you kind of commit to memory. Upper half of a hemisphere, radius 1, left half and right half of a circle of radius 1, which means that would fit flush when you connect them to the xy plane. Yes, sir?
If our x had a plus or minus y squared in there, would that be a hyperboloid?
If this were added, yes. That would be, hold up.
Would be under some weird shape.
I gotta do my traces. If that were a plus and z were 0, you square here, y squared minus, that's a hyperbola in the xy plane. So that would turn out being a hyperboloid of 2 sheets. Like that. The bowl this way and the bowl that way. The hyperboloid of 1 sheet is the one that looks like your cooling towers at power plants.
You're talking about opposing Pringles.
The Pringle is the hyperbolic paraboloid.
Oh.
That's the saddle, yeah. So, all those things are note card worthy. Did y'all make note cards for those? Nah, not so much.
Can we take notes on the test 4?
Can we yes. The test 4 is open notes, especially this next chunk of material on the surface integrals and the flux and the vector fields. In the past, I've usually let students take, like I'd give quizzes on that material and they could take their quiz work with them to kind of refer to. I'll just simply make it an open notebook test. But we're going to take it in here, remember, because it's taken on final exam night. Anybody want to just take tests? I mean, I'll want to be here that night for the test. I mean, so I figured the majority of you would want to take it in here. Anybody just have a conflict and want to take it in the testing center instead? Well, okay, I know.
What day is our final on?
It's on that Tuesday, May the
5th or 6th?
5th. Yeah. I forgot how to talk. May the 5th. I think it's that Tuesday night.
It
So
is.
2 weeks from this past Tuesday night.
Day before Father's Day.
Yeah, no, May the 5th is.
It's the day after.
It's the day after. May the 4th be with you, remember?
Did you see the new trailer?
May the 4th.
No, but I shared it on Facebook. I shared it with myself earlier so I could watch it because today began at 6:30 and it's been a continuous day until right now. But I want to show you, anybody want to see those spherical conversions real quick?
Yes, please.
Okay. If class is over, if you don't care to see them, you're not going to hurt my feelings. Although I'll probably remember it. But anyway, you're not going to hurt my feelings. If you're curious to see where those spherical conversions come from, feel free to stay, and I'll be glad to show you. Well, actually, let me just take out the picture, my little lane picture I showed you earlier. Okay. And color code this to help. Hey.
Just so it's true, testing is still open.
Yeah, test is in there for tomorrow and Saturday.
Okay, got it.
Only a handful of folks, the majority of everybody still has yet to take it, so they'll be there for Saturday.
Thank you.
Okay, so I've got, this is a, oh, I'm sorry. Go back to my document camera. This is just any random row coming from the origin out, like one of those rubber bands in the push ball, or like a single projectile from a fireworks explosion.
Okay.
And I'm going to project this down to the XY plane this way to make a right triangle. So there's a skewed right angle right there where that vertical Z line hits the XY plane.
Yeah.
Okay? But in the XY plane, I can also project this to the Y axis. There's going to be lots of skewed right angles in this image. And I want to project this to the X axis to help see how my conversions work out. Okay? So, oh, and I also need one more projection. I need to go from the tip of rho here all the way to the Z axis, as close to parallel as I can see at the bottom. Okay. So you kind of got this little angled plane coming out of the Z-axis where rho is. So rho is stuck in that plane that's outlined in red and blue. And then that projects down here to the XY plane, and those go to the XY axis like that. Okay? So if I want to project, and also there's a right angle right here. So there's 1, 2, 3, 4 different right triangles in this image. All right? The one where you... That's okay. The one where you project rho onto the Z-axis right here. See, going from here due north, that's a Z coordinate for XYZ. So what trig function would project that rho onto that for like its adjacent side?
It's going to be cosine.
Cosine. So if I multiply rho times cosine of phi, that'll essentially give me that Z coordinate right there. That Z distance is rho cosine phi. And that, my friends, is the easiest one. Rho times cosine phi gives you the Z value for Z coordinates, okay? Now, I want to project rho to this red dotted line down here in the XY plane. But keep in mind, this is a rectangle. So this blue dotted line up here is the same distance as that red dotted line down there. So if I wanted to use phi to project this up to here, what trig function of phi would project the hypotenuse rho to that opposite leg? Sine. So just like rho cosine phi projects it onto the adjacent for phi, if I want to go to the opposite phi, I do rho sine phi, and it projects it up there. So
now you got a traditional hypotenuse on the XY plane.
Yeah, because this blue distance is the same as this red distance down here. Yeah, from rho sine phi.
So for X, you use cosine, and for Y, you use sine.
So if you can understand this, you'll never forget the spherical conversions. Because now that this is projected down here to the XY plane, this is like a hypotenuse for this blue right triangle. So to get the adjacent side for theta, I need to use cosine of theta times the hypotenuse. So I need to multiply cosine theta times rho sine phi to get the x distance right there. So this x distance, so rho sine phi times, cosine theta projects this to the x-axis, just like when I want to project this to the y-axis, or to this blue line, I would say hypotenuse times sine theta to get that distance as a projection. So rho sine phi times sine theta gives me the y coordinate. Didn't take too long.
No, that's not that bad. I thought it was
No, that's way more simple.
Okay. Well, the picture helps out.
Yeah.
And almost any calculus textbook that tries to explain this probably draws that exact same picture, because that's just how I committed them to memory.
Yeah.
Yeah, cool. Okay.
Watches.